Okay, let's start our first afternoon session. Our first speaker today is Jacques Verstraete from University of California. He's the awardee of the Frontier Award of Science this year, and he's going to give a talk about recent progress in Ramsey theory. Let's welcome.
Thank you. So let me begin then with an outline. So I won't assume too much. I'll start off with some classical Ramsey theory. I'll then say a few words about random graphs. The new part and the new approach to Ramsey theory that I'm proposing in this talk uses pseudorandom graphs. So I'll define what that means as well. And then I'll talk about these central quantities in Ramsey theory, which are called Ramsey numbers. And the new progress is to almost asymptotically determine this Ramsey number R for T. There's a few other applications of this method, in fact, many that I can't go through in this talk, so really I'm going to just end with a few open problems there at the end. So let's talk about a little bit about classical Ramsey theory. So what's it all about? So the general philosophy of Ramsey theory is that in any sufficiently large structure, there is a relatively large uniform substructure. This is very vague, so I'll quantify it in a second. Another way of saying it, a few people have said this, that in mathematics, perfect disorder is impossible. So let's quantify what I meant in this first statement. So if I give you integers s and t at least 2, then RST is the classical Ramsey number. What it denotes is the minimum number n such that no matter how you color the edges of a complete graph on n vertices, let's say red and blue, you will either contain a red complete graph of order s or a blue complete graph of order t. So these numbers RST quantify that first statement. How large uniform substructure can you get in this case in the sense of graphs, coloring graphs? So those are the central quantities in Ramsey theory. As I said, they are the classical Ramsey numbers. As an elementary exercise, we could all check that R of 2t is t if you color a complete graph on t vertices. Either you get a K2, which is red, means there's a red edge, and if there's no red edge, the entire thing is blue, and that's your blue KT. So R2T is clearly equal to T. That's about the end of it in terms of determining what these things are exactly. There are a few cases, finitely many, which are known. Perhaps the most celebrated and early one is R33 is 6. That's a nice little problem for students. Why it's 6? Well, what do you have to do? You have to come up with a coloring on 5 vertices that avoids the red triangle and avoids the blue triangle, right? That's what R33 bigger than 5 means. It means there is a coloring that avoids both of those triangles. And a moment's thought tells you that there is a coloring. In fact, it's the only one. It's that. Now, I'm sorry if the red is not too visible. There's a red pentagon and a blue pentagram there. And clearly there is no blue triangle and no red triangle. So R33 cannot be 5. To show that it's 6, also not too difficult, so we have 6 points now. And we want to say no matter how you color, you will find a red triangle or a blue triangle. Why is that? Well, if you pick any one of the points, there are 5 edges going out, right, to the 5 other vertices, which means that 3 of those edges at least have the same color. Let's say 3 of the edges on that vertex have the same color. Let's call them red. So you get 3 edges like that. And now, if you look at the neighbors of that vertex, if any 2 of them make a red edge, you're done. That's a red triangle. Okay, so that's what you get there. There's your red triangle. Otherwise, if none of them is red, well, then you have a blue triangle, right? So that's the nice little argument that shows that R33 is 6. And the reason I mention that argument is that is the argument that shows that R of ST exists. So these numbers were actually, they come from a paper of Ramsey from the 1920s, but it is a task to show that these things exist, that this is well defined, that RST is a finite number. And that argument I just gave works in general. I'll say a bit more about that in a minute, but before I do, there are only 6 other R3Ts that are known. There they are, right, up to R39. So R310 is already not known. So that's what I just said. Now, what about the R4 numbers? Well, R44 is 18. Actually, there is a beautiful construction for that from the 50s called the Paley graph. I'll say a bit more maybe about that later. And R of 45 is 25. Now, that doesn't seem to have any rhyme or reason behind it. If you look at the colorings on 24 vertices, which avoid what? A red K4 and a blue K5, they're pretty chaotic. There's no sort of nice way to describe those coloring. In fact, there are 30,000, more than 30,000 such colorings, and they're hard really to say anything about them. There's a picture for R34 is 9. Right? So once again, that's a coloring on 8 vertices, which avoids a red K3 or a blue K4, red triangle or blue K4. So that's R34 is 9, and there are these 2. So there's the actually beautiful construction to show that R44 is 18. Well, there's an example of the R45, and I'm going to shamelessly reuse Noga Alon's joke that clearly one can see there is no red K4 or blue K5. A moment's thought. Very long moment, though. So that's it, basically. R55 is not known. So these Ramsey numbers are very difficult to determine. There's a lot of computer searches. Unfortunately, the power of computers is insufficient to determine these Ramsey numbers, the large ones anyway. So what can we say in general? Well, as I said, these numbers exist. That was proved in 1935 by Erd H and Szekeres, who gave the following recursive inequality. And that inequality, if you think a little bit about it, is exactly the same argument as what I did for R33. Namely, you pick a vertex, it has lots of edges of one color on it, and now you look at the neighbors of that vertex. And you reduce one of the parameters by 1. Yeah? That's the inequality, and if you solve that recurrence equation, you get s plus t minus 2, choose s minus 1, which for this talk will just be important to know that if you fix s for each number s, this is less than about t to the s minus 1. So it's a polynomial of degree s minus 1 in t. So for example, R3t, I listed a few of them before. This is saying it's no more than about quadratic. It doesn't grow more than quadratic. So we can't determine these numbers, so what we're interested in then is their growth. What are they looking like asymptotically? So, one can improve the Erd H Szekeres theorem using some more advanced technique, namely using the probabilistic method. There's a beautiful argument. It's a truly magical argument due to Scherer from the 80s that shows, in fact, that RST is not quite a polynomial of degree s minus 1 in t. In fact, it's less than that by polylogarithmic factor. Okay, so this is related to lots of other problems. If anybody is interested in any of these kinds of problems, I can speak to you afterwards if you're interested in the connections. Many other problems in many different areas of mathematics, even more. So what about lower bounds? So this is the case of trying to find constructions of colorings, right? How do you find on a large set of points a coloring that avoids these uniform substructures? So it turns out the state of the art for R3T is that indeed it looks almost quadratic. It looks like t squared over log t. And in fact, that matches the preceding bound that I mentioned. So even in the polylogarithmic term, this is the right answer. This, to get the 1/4 there, is a major piece of work. It's more than 100 pages of mathematics. It was published in the memoirs of the AMS by first Pontiveros, Griffiths, and Morris. How do you get that construction? So what one considers is something called the random triangle-free process. So you add edges one by one to build a graph, but you condition on the event that there is no triangle created. And you just let that process run as far as it possibly can. By the time you get to the end of that process, that defines your red edges. Everything else will be blue. And the point is to show at the end of that process, it gives you this. That requires a pretty detailed martingale analysis. That process is by no means easy to analyze, unfortunately. Okay, so that's the R3Ts. R4T or R4N, one can do the same thing, right? One could sort of add edges to a graph one by one while not creating a complete graph on 4 vertices. This is the random K4 free process. You can see how long that goes. It goes to about t to the 5 halves. That's about how far it goes. So that's the bound it gives you on Ramsey number, something like t to the 5 halves. But the Erd H Szekeres theorem says this should be almost cubic, right? T to the s minus 1 when s is 4 is cubic. So unfortunately, the random graph approach doesn't seem to get there. And in fact, you can show it does not get there, at least not with any detectable probability. So the conjecture of Erd H was to prove that this number is roughly cubic divided by polylog. That was in papers from the 40s, posed as a conjecture, and we proved that conjecture, that in fact, apart from the polylogarithmic factor, it is about cubic. And the proof of this theorem, the main point I hope to convey in this talk, is that it changes the direction of Ramsey theory in the sense that random graphs are indeed no longer to be considered in this world. They do not give good constructions. In fact, there's been heavy analysis over the last 20 years of the random KS free process, which is even more involved than the random triangle free process. And it is shown it doesn't come anywhere near the upper bound given by the Erd H Szekeres theorem. So here, for the first time, we get that. And the philosophy will be, instead of random graphs, the philosophy now will be that good constructions, good Ramsey graphs, they hide inside pseudo-random graphs. And I'll say what I mean by pseudo-random in a moment. Fortunately for us, while they hide, they don't hide that well. Right? We can still find them, even though they're hiding. So, one could also define graph Ramsey numbers, which is to say, I want to get either a red copy of a graph F or a blue copy of a complete graph of order T. And for that, you can get some some bounds as well. This is perhaps one of the most tricky open problems to determine what it is for a cycle of length 5. So for these kinds of problems, we also get some new results. So I won't say too much about this. The point is that the general approach impinges on many of these Ramsey-type problems. So let's just move on. That perhaps I didn't know I had proved this. I discovered it online. The key to a successful party is a good mix of people. Well, okay, so maybe that's actually the deepest theorem in the talk, because I'm not actually even sure what that means. Even worse, I'm not even sure how it exactly relates to the Ramsey theory that I'm talking about, but okay. So that's interesting, I guess. Let's talk about random graphs. So that's supposed to be a random graph, I guess. And usually what one considers here is a very simple model. It's called the mean field model sometimes, or the Erd-H model of random graphs, where you flip a coin with probability of half, you get an edge of one color. With probability of half, you get an edge of the other. There's just a picture. And this was one of the early breakthroughs in the probabilistic method due to Erd-H, that there is a graph with exponentially many t vertices with no clique or independent set of size t. Right, so that's equivalent to saying RTT is bigger than square root of 2 to the t. There's no known explicit construction. This comes from, as I said, random graphs. And so how does that compare to Erd-H when S is equal to t? Well, RTT is less than about 4 to the t. Right? You can check this binomial coefficient is less than 4 to the t easily. And the construction was square root 2 to the t, so there's a gap there. It's a fairly big gap, and that gap is, seems to be very difficult to close. In fact, that's a major open problem due to Erd-H. Show that R of tt to the 1 over t actually exists. This problem at present seems utterly hopeless. However, there was a major breakthrough last year in showing that RTT is not 4 to the t. It does not match the upper bound of Erd-H and Szekeres. It's actually 3.99999 to the t. I'm not sure if I have enough nines there, but the gist of it is clear. So what this RTT is, nobody knows. What about explicit constructions? What if we don't use random graphs? Well, there's a famous theorem which started a whole line of research into explicit constructions. That is the Frankel-Wilson theorem, a very simple construction which gives something like 2 to the log t to the c. And there have been improvements of this, but nothing close to the upper bound. So at the moment, there's no explicit construction, no, that is exponential for RTT. So that's enough for now about this RTT. We want to consider RST, and I said pseudo-random graphs would help us in that endeavor. So we all know, and fortunately there have been preceding talks, so this is almost like a refresher. You can take for a graph its adjacency matrix, put a 1 where there's an edge and a 0 where there isn't. This is asymmetric matrix, so you get something like that. There's a picture. For every graph, you can associate its adjacency matrix, which has eigenvalues. And they're all real, of course, because the matrix is symmetric. And in the case of random graphs, they should maybe look something like this. I won't be too specific about what I mean by random graphs. There are some conditions on Wigner's law. But normalized eigenvalues spectrum should look like this. And so given any graph, I can look at its spectrum and ask, how does it compare to this? So one simple thing I could do is, if a graph is d-regular, then of course its largest eigenvalue is d, because the all-one eigenvector exists there. So what we should look at is the other eigenvalues. And let's say the graph is an nd lambda graph, or lambda pseudorandom, if all the eigenvalues of the adjacency matrix, except that largest one, at most lambda. The Alon-Bopana theorem, which we have heard in some previous talks, says that that number can't be less than about 2 times the square root of d minus 1. In fact, this statement that I've written here has a very beautiful short proof, almost completely combinatorial by Noga Alon. The error term is 1 over the diameter, essentially. So we can't get less than about the square root of d for that, all the eigenvalues apart from the largest. What's the point of doing this? The point is you can explicitly relate combinatorial properties of a graph with the spectrum of its adjacency matrix in an extremely simple way. Namely, if you consider twice the number of edges inside any set X of vertices in such a graph, that's exactly the inner product of AX with X. A is the adjacency matrix, X is the characteristic vector of your set. And that should be clear because really what you're doing is you start with X, which means you're in the set. AX says take one step. Walk one step, that counts an edge. And you have to land up back in the set. By definition of inner product, so that's that. Oh, so the distribution of edges in sets is explicitly related to this. But X, being a characteristic, being any vector, I can expand it in terms of an orthonormal basis of eigenvectors. And that brings the spectrum of the adjacency matrix into everything, namely in that way, right? So you just let xi be the coefficient of x with respect to the ith eigenvector. This is an explicit way to write the number of edges in a set X in terms of the eigenvalues. And the largest eigenvalue is D, as I said. So you get this equality, it's an identity. And then on the right, we just said all the other eigenvalues are at most lambda in absolute value. So you can immediately bound them. And this is what you get. And you just use the first coefficient of the first eigenvector with x is size of x over root n. So what we have here, let me go a bit closer, is that the difference between twice the number of edges in any set and the number of edges you expect in that set, as though that set was of certain size, was chosen randomly amongst all sets of that size, this deviation from what you expect is explicitly controlled by that number lambda. This is sometimes called the expander mixing lemma. Very, very useful result, but as you just observed, it doesn't really use much except basic linear algebra. And in fact, you can write it like that in terms of the smallest eigenvalue, lambda n, if you like. But the point is, we said these graphs are lambda pseudorandom, and now it makes sense why. Why are they lambda pseudorandom? Because if lambda is the bound on all the eigenvalues but the largest, then that controls the distribution of the edges. They should be fairly close to what you expect. Now, this is a talk on Ramsey theory. So what we really want to do is talk about independent sets. If I give you a graph, let's say a lambda pseudorandom graph, and I give you a set of vertices with no edges in it, that's an independent set. And what I want to know is how big that can be. Right? This is clearly where all the blue edges are going to make a clique if I were to consider the complementary graph. So this is Ramsey theory. Now, it's easy to see that the number of independent sets in any d-regular n-vertex graph is at least about d plus 1 to the t. If you take a disjoint union of complete graphs, that's tight. So we can't do much if I just give you any d-regular graph. However, one of the remarkable theorems due to Alon and Erd is that if the graph is lambda pseudorandom, you can do much better. You can count independent sets in a much better way. Let me give one little sort of interesting thing that you could do with pseudo-random graphs, just to motivate. If I have a set of prime numbers up to n, let's say m of them, and I tell you that every integer up to n is a sum of 2 of those primes in some number of ways. Let's say the number of ways you write an integer as a sum of 2 primes in your set doesn't deviate much. It's sort of always the same, no matter which integer you pick. Mod n, though, right? Because otherwise you have problems near the ends. Let's do it mod n. Then, in that case, you can find a lot of 3-term progressions of primes in that set. So that's kind of remarkable that some sort of counting thing would give you that. Now, is that true? What if p is all the primes up to n? Is that true? Well, not quite, right? As we know, the number of ways of writing integers as sums of primes depends very much on the arithmetic properties of that integer, right? How it factorizes into primes, for example. So there could be some big variations if you take all the primes. Now, the Green-Tau theorem says that in the case of 3-term progressions, that there are lots of 3-term progressions in the primes. Now, not only infinitely many, but in fact you can count them nicely. But the problem is that the primes don't have that property that we would like them to have to immediately imply the first statement. So what they do instead, and you can read their thing, they make heavy use of this regularity lemma, or transference of the regularity lemma into the primes, to kind of cheat a little bit and trick the primes into having the nice property that you get some pseudo-randomness. I won't say any more about that. It's not the focus of the talk. The main point is it comes from defining this graph where you join x plus p to x plus 2p mod n. That's all. You look at that graph. If the first property holds, then in fact that graph is lambda pseudo-random for a nice lambda. And if that happens, large sets have lots of edges in them. That turns out to be enough to give you lots of 3-term arithmetic progressions. If you're interested, I can show you how after the talk. I drew a picture of such a graph. Well, from far away, it looks like a blur, so I guess that means it is pseudo-random. And in fact, you can find a lot of 3-term progressions in this graph. They correspond to kind of paths of length 3, but I won't say much more about that. Let's go back to Ramsey numbers then. So, consider, let's say, an n d lambda graph that is triangle-free. What can we say about the spectrum in that case? Well, the sum of the cubes of the eigenvalues is 0, right? Because the trace of the cube of the adjacency matrix is 0. These are closed walks of length 3. And if that's the case, then you immediately get this inequality between n, lambda, and d. N is the number of vertices, d is the degree, and lambda is the bound that you get on all the eigenvalues but the largest. So you immediately get this bound. And we also said by Alon-Bopana theorem that this lambda cannot be less than about root d. So the best you could do for a lambda pseudo-random triangle-free graph with lambda's root d comes from this inequality. If you solve it, it tells you d should be about n to the 2/3, lambda should be about n to the 1/3, and that's the best you can do. So there it is. We'll call this spectrally optimal pseudo-random. So it's a triangle-free graph with those parameters. And in fact, these were found in 1991. A beautiful construction of Noga Alon found a triangle-free graph with those parameters. Later, a slightly different construction was given by Swastik Koparty. And in fact, you could define spectrally optimal pseudo-random KS-free graphs. By just continuing the argument with the trace, you can show that there are these parameters for an optimal KS free pseudorandom graph. Now, why are we going on about these things? Because if you had these, you would have Ramsey numbers. RST would be that polynomial of degree s minus 1 in T if you had an optimal pseudorandom Ks free graph. So that's a theorem, and it comes from counting independent sets. The idea is very simple. You take your optimal pseudorandom Ks free graphs, you count independent sets of a certain size, there's not too many of them, you then randomly sample in that graph to kill them all. And so what you get then is a subgraph that has no large independent sets and, of course, inherits the Ks-free property, which means that the nice Ramsey graph is hiding in the pseudorandom graph. How do we get these things? So here's a general approach, which we use successfully. Start with the point line incidence graph of some geometry. This is a bipartite graph, let's say with two parts, A and B. And what I'm going to do, I'll just say it in words. You have your point line incidence graph. I will project the graph down onto one side. What that means is on one side, you put an edge between two vertices if they have a common neighbor on the other side. So it's like the square graph. You push it down onto one side. Now every vertex that was at the other side projects down to a clique. Right? All its neighbors are joined. So you get these cliques, and they're edge disjoint if it's a point line incidence graph. So you've got this graph that's constructed as a bunch of edge disjoint cliques. The next step you do, of course, a clique contains every graph. A big clique will contain every graph, so we don't like big cliques. If we're trying to do Ramsey theory, you simply now randomly cut those cliques in half. So in each of those cliques, slice it and take a random complete bipartite subgraph. So that's what I'm saying in these next 2 points. You project it down. This is a union of some cliques. And then in each clique, we're going to do this random bipartite subgraph. So there's that. We'll call that G pi star. And I call that random block construction. So it's a fairly simple construction. It is still a random graph, right? But it's not the same kind of random graph as we had before. In fact, it has fewer random bits, if you think about it. Fewer random bits than Gn1/2. And then we do what I alluded to before. Once you have that random block construction, you now sample vertices in that construction to destroy the independent sets that you don't like. And we're going to do that in a particular case. This is what we did so far. Bipartite graph, project down, random cuts in those cliques, random sample. So you start with that, right? You project down, so you get a clique for every vertex at the top. So you get all these cliques from the vertices on the other side. There it is. There are these cliques. We then cut them in half. Right? That's G pi star. So there we go. And then you randomly sample. Okay. I should do that again because it's kind of fun. But yes, you independently and randomly sample vertices, but with a suitable probability. That's right. So let's do this, since it's an example I mentioned at the start, to show it's about t cubed, Ramsey number 4t. So we're going to do this thing again, but we need to know what the graph you start with is. The graph you start with is the bipartite incidence graph of a rank 2 geometry of points and lines. And this is called, in projective geometry, the Hermitian unital. I'll say more a bit about what that is. The point is that that Hermitian unital, you could consider it as its bipartite incidence graph. It avoids certain structures, and that is what we're looking for in Ramsey theory. We want the bipartite graph you start with before you push down and do all these things to avoid certain configurations. And that will mean that the graph at the end will avoid some other configurations. So I'll say a bit more about that in a minute. You then do this projection, which turns out to be pseudorandom. It has these cliques. You then do the random blocks, which is cutting these blocks randomly in half, and you want to show that it's still pseudorandom. Now, to do that is not entirely trivial, and in fact, we have to use martingales to do that. We use Hoeffding's martingale inequality to do that. But once you have that, then by the other theorem, the number of independent sets of a certain size is not big. That's why we randomly sample at the end to kill them. Okay, so what is the Hermitian unital? There it is. So we consider projective plane of order q squared, square order, and we'll just consider the points on that variety. So it was proven by Michael Onan a long time ago that such a configuration does not contain 4 lines in general position. This is nothing short of an utter miracle, that it doesn't contain 4 lines in general position. And I'll show you a picture of that in a moment. However, the proof was heavily algebraic, in fact, group theoretic. There is a very short proof that there are no 4 lines in general position, and I can even show it to you. Let's define this form. Given 2 elements A and B in FQ cubed, all of this, of course, being over a finite field of order Q squared. So consider 2 points A and B in the Hermitian unital. You define this, this form. And so now let's have a look. Because you're in the unital, sigma of AA is 0. That's the definition of the unital, actually. And in fact, using the fact that if A plus B is in the unital, sigma A plus B is 0, that tells you this is skew symmetric. Okay? That's all we need, in fact. Let me draw the picture. There are 4 lines in general position. This is what we want to say does not exist in the unital. I labeled the points A, B, C, D, E, F. I hope it's visible. That what is true, this is called the Onan or Pasch configuration, is that I can choose representatives for these vectors so that D is A plus B, E is A plus C, and F is A plus B plus C. So that you just have to believe that that is possible to do. But once you have that, we're in good shape. So this is what I just said, right? We can choose generators so that this occurs, and we want to avoid those 4 in general positions. So make the matrix 3 by 3 matrix whose rows are A, B, and C. So of course that matrix is not singular because A, B, and C are not collinear, right? Similarly, the matrix B, whose rows are A to the Q, B to the Q, C to the Q, also is non-singular. That's not hard to prove because of the math x goes to x to the q. So AB is not singular. But AB is singular. Why? Just compute the determinant. The determinant is this. This is AB. This is the determinant. But remember, D is A plus B, which is an element of the unital, which means that sigma is skew on AB. Sigma AB is minus sigma BA. And the same for BC and CA, so these cancel. That's it. So there are no 4 lines in general position. And what does that do for us? Well, if you start with the bipartite incidence graph, what are we going to do? We push it down. If we push it down, that means no 4 of the cliques pairwise intersect. That would correspond to the 4 lines in general position, pairwise intersecting. And once you have that, the final graph that we get when you take these random cuts and all that has no K4 in it. So that's the key fact. I want to end with a couple of open problems. One thing I said is that we count independent sets in pseudo-random graphs to get these results. The independent sets you can count are of size Cn log squared n over d. And the number you get explicitly is this number with a squared over here. So this is actually not too hard to do now with the modern method of containers. There's a new method in combinatorics that's used for solving many problems that were unsolved before. It's called the method of containers, and it gives this result. But it seems that that log squared n should not be there. It should just be simply log n. So you should be able to count. You can't count independent sets of size n over d in a good way because you can just generate them however you like. But n log n over d, you should be able to count. And if you were able to do that, you would get, in fact, the order of magnitude of these Ramsey numbers R4T. Not only that, it would tell you that the optimal pseudo-random KS-free graphs exactly match the upper bound that you get from the theorems I've said before on RST. So saving an extra log n there, it seems like a mysterious thing. In fact, given a lambda pseudo-random graph, you can ask this question: is it always true that you can save this log factor? We don't know of one where you can save the log factor. So that's a bit disturbing, right? So you could ask, is it true for all of them, but can you even prove it's true for one of them? Of course, another thing to do would be to consider those other Ramsey numbers. What if we try the same approach as we did to get this R4T for R5T, 6T, 7T? Now, there things get more and more difficult. In particular, if you wanted to use a similar approach to this Hermitian unital, you would need a set of points and lines where no 5 lines are in general position. And a good place to look would be in the projective plane of order q cubed. Just the numbers work out how you want over there. The problem is that it seems, in fact, it's true, that if you were to find such an optimal set of points and lines, then it would somehow require you to find an optimal pseudo-random K4 free graph. And that we do not know how to do. These optimal, spectrally optimal pseudo-random graphs, we don't know how to do. And yet, this kind of construction, which says nothing about optimal spectrum, seems to require it. That's for R5T. So 5 lines in general position look like that. Right? There's an extra line cutting all 4. So unfortunately, that's open. I won't say much about the last open problem, so I guess I'll just end with that picture. Thank you.
Thanks for your great presentation. Now, questions?
Where does the idea of owner configuration and permission unit come from?
Where does it come from?
Where the idea
Well,
come from?
it comes, so as I said, it comes from, certainly comes from projective geometry. In fact, in the paper of Michael Onan, it was not one of the central things. This is very strange how this happens in mathematics, right? Where an offhand remark or a small little piece of a paper can turn out to be extremely important for future mathematics. And that's the case with that Onan configuration. It was just a side remark, really, that was made to show that you don't contain this configuration. And also, I should say, there are entire books on what projective geometers call unitals. Unitals are not uniquely defined in mathematics. There's other notions of unitals in other areas. But in the projective geometry version, there's a book by Barwick and Ebert, which is entirely dedicated to unitals. So, of course, what we wanted to know is what other constructions there are. The Hermitian unital is the only one that doesn't contain the 4 lines in general position. So it wasn't a central aim back then to actually discuss 4 lines in general position, but it is miraculous that this construction does not contain it. But unitals are used, for many, many other things in projective geometry. They're used for constructing other kinds of geometries, for example. I can only refer you to the book. If you want to know more about unitals, there's a whole book, a really thick book on them. So, yeah.
Can you say something about how you go from this not having 4 lines in general position to this lambda pseudorandom of the subsample graph?
Yes. So probably it's better if I just use some chalk, and I'll be very brief. So if you do not have 4 lines like that in the geometry, then what you get in the incidence graph is you do not have 4 points such that each pair has a common neighbor, right? Which would look, say, perhaps something like that. Right? So this structure does not appear in the instance graph because this is not in the geometry. Now, what did we do? We projected down, right? So it means we now look at a graph over here where there's a bunch of cliques, one for each vertex up here. That graph down there turns out to be what is called a strongly regular graph. Every pair of adjacent vertices has a certain number of common neighbors, and every pair of non-adjacent vertices has another number of common neighbors. Strongly regular graphs are a huge topic in spectral graph theory. In particular, they only have 3 eigenvalues. There's the largest one with multiplicity 1 in this case, and then there's only 2 others. The 2 others are lambda 2 and lambda 3, and they look something like this. And they are determined, if you think about it, really from that fact that pairs of vertices have fixed numbers of common neighbors. You can take the square of the adjacency matrix and write a polynomial equation to get all the eigenvalues, and there are only 3. In particular, this one, which I should have called lambda n, it's the last one, it has a certain multiplicity. It is minus q, and remember I said from the expander mixing lemma, that tells you distributions of edges in large sets of vertices. So this is perfect for us. There's one problem, and that is this is not the graph that we want. The graph we want cuts those cliques in half. And you'll observe that if you do that, that greatly affects this eigenvalue. Because in fact, when I cut these cliques in half, I get large, complete bipartite graphs in there, which turns out to make this thing drop through the floor, unfortunately. It goes down to like minus q squared or something. So that's no good. But that doesn't mean that the pseudo-randomness wasn't preserved, right? So that's what we do. We say the pseudo-randomness that you had here, using some martingales, is preserved even after you do these cuts. We were deceived for a while into thinking maybe we should try to say something about the eigenvalues once you've done the random cuts. And the answer is no, don't say anything about those eigenvalues. They do not work. They are not what you want them to be. Does that? If you don't do the random cuts, then let's look at this picture. What does this picture say? It says that I cannot have 4 of these cliques making a complete graph of order 4. So maybe I cannot have that picture. But I want the final graph not to have any complete graphs of order 4, and therefore I will cut the cliques in half. Because what this says is that a complete graph of order 4 has to put a triangle, at least, inside one of these cliques. But if I cut them randomly in half, there will be no triangles in there. And so that is the purpose, to destroy those K4s.
Hello, Professor. Thanks for your beautiful talk. My question is, can we use mathematical logic to study like Ramsey theory? Because I know that Ramsey theory is closely related to set theory. And actually, there is a proof in model theory that the Ramsey number exists, right, in like the most general case. So I wonder if there is any recent progress in this, like we can use model theory to study like Ramsey theory, like this. Thank you.
That's a good question. So in this talk, I focused on graph Ramsey numbers for simplicity. But you can actually define this in general, right? The philosophy I mentioned at the start was that in any sufficiently large structure, there's a uniform substructure. I didn't mention graphs when I said that. So you can do that for sets, right? So it's known, for example, if you color the subsets of size R in a large enough set, you will get, again, these monochromatic cliques. So indeed, Ramsey's original motivation was from logic. That is true. The focus on Ramsey theory from the logician's point of view is mostly in the infinite environment. Here, we're interested really, because we're in combinatorics, in quantitative bounds. In logic, they're not so interested in the quantitative bounds, more in the infinite world. Yes, sorry, I interrupted.
Like logic can, like in this theory, it can only give like qualitative like things, like there exists a Ramsey number like this.
Right. So to be honest, I'm not an expert on this, but I'm not aware of any proofs from logic that actually give you concrete bounds on these Ramsey numbers. And as I said, there's a lot of Ramsey theory that I haven't mentioned here for infinite sets. You know, what happens if you color, you know, subsets of the continuum, for example? When do you get monochromatic substructures and when do you not? Yes. So I don't know of any progress from that side. Thank you.
Okay, maybe we can stop here. Let's thank our speaker again. We will resume our afternoon section in 20 minutes.